Thank you. Yes, thank you very much for inviting me here, and it's my great honor and pleasure to come back to Boston and give this talk. So today I'm going to talk about diffeomorphism group of four manifolds, and in recent years there has been some new developments in studying these classical objects relating to configuration spaces. So I want to talk about these new developments, which are very exciting, and our attempt to better understand them. Yeah, and as you can realize, there is a typo on the very first page, developments. So yeah, so I can imagine there will be more typos or mistakes. So if you find any, please correct me. Okay. Yeah. Or if I say something silly, please correct me. Okay. Yeah. So first, maybe let me set up some notations. In this talk, we let M be a smooth manifold. We always assume M is compact, oriented. We do allow M to have a boundary because later we want to talk about M is a four-dimensional disk, which is one of the most important case. And so now we consider this diffeomorphism group of M, which consists of all orientation-preserving diffeomorphisms that equals identity on the boundary. Some people use different notations. They put a partial here and there to indicate that we are thinking about diffeomorphisms relative to the boundary. But I feel, so I'm just ignoring that. So this space can be equipped with C infinity topology, making it into a topological group. And historically, there has been two main streams to understand this object. One from algebraic perspective, namely studying diffeomorphism as a group, studying the group structure on this object. Like we want to understand what are the subgroups of this diffeomorphism group, what are the quotient groups. And for example, the famous Torelli problem is the famous Nielsen realization problem is in this direction. Okay, but today's our main focus will be the second perspective, studying the topological property of this space. Okay, diffeomorphism group. So in particular, we want to understand is it path connected? How many path components does it have? And even better, we want to understand at least partially what's the homotopy type of this diffeomorphism group, and maybe we want to say something about its homology. Okay, yeah, and so that's today's focus, and our main focus today will be dimension 4. So this is a dimension in which you can use different techniques from lower dimensions or also from higher dimensions, or some techniques which are special in 4 dimensions, but still. This object is still quite mysterious in this dimension. Okay, so maybe let me talk some motivations to study this object, because you may ask, why do we care? There are several motivations. First, understanding diffeomorphism group help us to classify manifolds, but not a single manifold, but a manifold in a family setting. So for example, if you think about a smooth fiber bundle with fiber M and with base B, you can sort it as a family of manifolds parametrized by the base space. Okay. So now if we want to classify fiber bundles, we are basically thinking about classification problem in a family setting. And recall that we have this universal bundle over this classifying space, and every smooth bundle is actually pulled back from this universal bundle in a unique way. So there is a one-one correspondence between smooth fiber bundles with a given fiber and a given base, and the other side is just the set of homotopy classes from A to B diff. Okay? So B diff is the classifying space for this topological group. Okay. Yeah. So basically, in other words, by studying the homotopy type of this classifying space, we can study the classification problem of smooth fiber bundles. And in particular, if we think about elements in the cohomology ring of this classifying space, those elements correspond to characteristic classes for manifold bundles. So because every bundle is pulled back from the universal bundle, so you just set the characteristic class of the universal bundle to be a specific element in the cohomology of this classifying space, then you just pull back. Okay, so understanding this cohomology is basically understanding characteristic class for manifold bundles. Also, if you think about elements in the homotopy group of the diffeomorphism group, that basically correspond to the fiber bundles over spheres, because you can just glue two bundles together using this diffeomorphism as the clutching function. Okay, so you can take the product of M with two copies of disks and just glue them together using these elements in the homotopy group. Okay, so another motivation is that we can use diffeomorphism group to understand some additional geometric structures on M. For example, let's say if we consider symplectic manifold, then we can also think about the symplectic morphism group. And we also care about the space of symplectic forms in a given cohomology class. Okay, so let me denote this by S omega. Okay, and it turns out that there is a fibration relating the diffeomorphism group, symplectic morphism group, and this space of symplectic form, giving us a long exact sequence of homotopy groups. And so one can understand the space of symplectic forms by comparing the homotopy types between the symplectic morphism group and the diffeomorphism group. And I think there are a lot of exciting works in this direction by Seidel, Krauthammer, and Smirnov, and many other people in recent years. Okay, so yeah, so that's another motivation. We can use this to study geometric structures on the manifold. Okay. And maybe some more motivation. This diffeomorphism group is also closely related to smooth structures on manifolds. First, let's set out some more notations. We denote the homeo M to be the group of homeomorphisms, also orientation preserving, from M to itself, equal identity on the boundary. Then let's fix a smooth structure S0 on M, okay? And consider, so now, so I'm changing the notation a little bit. I'm using diff M S0 here, because I want to emphasize that this is a diffeomorphism. This is the group of diffeomorphism for a specific smooth structure. Okay, so and of course the homeomorphism group doesn't depend on S0. So we have a forgetful map because every diffeomorphism is also just a homeomorphism, and we have this forgetful map. And it turns out that if every continuous map, you can turn it into a fibration up to homotopy. Then you take the fiber called the homotopy fiber. The homotopy fiber of this map turns out to be homotopy equivalent to the space of smooth structures on M that are diffeomorphic to S0. Okay, this may sound a little weird if you haven't seen it, because when we talk about smooth structure, okay, what do we mean really? Okay, so one way to think about smooth structure is like, okay, we care about smooth structure up to diffeomorphisms, right? So if there is a diffeomorphism, between two smooth structures, we just think them as the same object. So that's one way to think about it. But here we are thinking smooth structure as a maximal compatible atlas, so basically charts. Okay, so if you have two different charts which are not compatible to each other, we do not treat them as the same object, even if they are related to each other by diffeomorphisms. Okay, so by doing this, you don't have discrete, you don't just get some discrete isomorphic class of smooth structure. Instead, you have a whole space of smooth structures. Okay? And we can try to understand the topology of this space. Turns out that this space is homotopy equivalent to the homotopy fiber of this forgetful map. So namely, if there is a difference between the homotopy of if this rho M for some reason it fails to be a homotopy equivalence, then there is some funny loops or holes in the space of smooth structures. Okay, yeah, and yeah, so that brings us to the question, is this a homotopy equivalence or not? Okay, is this forgetful map a homotopy equivalence? Yeah, we will address this question a little later. And also, I want to, yeah, so the mapping class group of M is defined as the path component of diff M. So yeah, so this is a very classical object, most well studied for surfaces. It can, the mapping class group of surface has become a huge subject in itself. Today we won't talk too much about it, but indeed it's a very important object, even in high dimensions. For example, let me mention one very important fact. Given a mapping class group, given an element in the mapping class group, so sorry, let me emphasize that here, when I say diff, I always mean orientation preserving diffeomorphism. Some people put plus on the notation, but again, let me just ignore that. Okay. So given an element in the mapping class group, we can form a smooth manifold by gluing two standard disks along their boundary using this diffeomorphism. Okay? It's not hard to prove that using the Alexander trick. It's not hard to prove that this is actually always homeomorphic to the standard n+1 dimensional sphere. Okay? So in other words, given a mapping class of n-dimensional sphere, we get n+1 dimensional manifold, which is homeomorphic to the standard sphere. And it turns out that in higher dimensions, this is actually a 1-1 correspondence. Oh, sorry, I think I made a mistake here. Here n should be greater or equal than 5, not equals to 4. Yeah, so n+1 is greater or equal than 4. So it also works when n equals 5. Okay, so elements in the mapping class group 1-1 correspond to smooth structures on n+1 dimensional spheres up to diffeomorphism. So, for example, as we know, there are 28 smooth structures on S7 up to orientation preserving diffeomorphisms. That means there are 28 elements in the mapping class group of S6. Okay, so yeah. So this is another motivation to study this diffeomorphism group because it has many connections with smooth structures. Okay. Yeah. Okay. And I want to, yeah. So if any question, feel free to ask anytime. Okay. Yeah. And I want to say that the techniques for studying this diffeomorphism group, it's different in different dimensions. For example, let's start with the lower dimensional case. In this case, the geometric and topological techniques are extremely powerful because you can visualize everything, like curves and surfaces. You can all draw them on the blackboard. So, so in this case, the geometric technique is very powerful. Also, you can use hyperbolic geometry in lower dimensions. For example, if we have a hyperbolic surface, a surface with genus grade at least 2, then it's a classical theorem that every component of this diffeomorphism group is contractible. Okay? So that means if you care about the homotopy type of this diffeomorphism group, the only thing you care is the path components, namely the mapping class group of the surface, which of course which is very interesting and has rich structures. You can study them using all kinds of different techniques. And also, same result actually holds for hyperbolic 3 manifolds. This is a deep result proved by Gabay. Each component of a hyperbolic 3 manifold of the diffeomorphism group of hyperbolic 3 manifold is contractible. So again, you just care about the mapping class group, okay, which is actually always finite. Okay, and some important results about the sphere. Any result about the sphere is important. So, so the mapping class group of the 3-dimensional sphere is trivial. That means every orientation preserving diffeomorphism on S3 is smoothly isotopic to the identity. And also, Hatcher proved that the diffeomorphism group the inclusion from the isometry group of S3 to its diffeomorphism group is a homotopy equivalence. Yeah, so this is the so-called Smith's conjecture in dimension 3, which I will talk more later in the talk. Okay. And also we know that for any 3 manifold, this mapping class group is finitely generated. So we do have some good understanding of this diffeomorphism group and mapping class group in lower dimensions. On the other hand, if you go up in dimensions, algebraic techniques are more powerful, because now you can use like surgery theory, and you have Waterhausen's work that relates this diffeomorphism group to algebraic case theory, and you can also use rational homotopy theory. All kinds of algebraic machineries are available in higher dimensions, because you have high dimensions, you have a lot of rooms to do surgery, to perturb your submanifolds. Okay, and for example, let me just mention one result which will be relevant for later discussions. Suppose we have a simply connected manifold. Then this mapping class group is common measurable with an arithmetic group. This is a very famous theorem by Dennis Sullivan, proved using rational homotopy theory. So in particular, this mapping class group is always finitely generated, okay? Just like lower dimensions. Yeah. And what happens in dimension 4? In dimension 4, it turns out that these techniques, geometric, algebraic, and gauge theoretical techniques, they can all be useful sometimes, but not always. And so you have many different techniques to try to study the same object. However, this diffeomorphism group remains very, very mysterious. For example, some very basic question. We don't have a complete description for the mapping class group of a single four manifold M. Well, here M, let's say M is compact. Okay, we don't know. We don't have for any single four manifold. We don't have a complete description of this smooth mapping class group. Also, we don't know whether the mapping class group of S4 is trivial or not. So, namely, does there exist a diffeomorphism on the four-dimensional sphere, which is orientation preserving, but not isotopy to the identity. So these are some very basic questions that we don't know. And today I want to talk about the dimension 4. And so my main focus there today will be some recent developments relating to configuration spaces. However, I want to spend some time talking about gauge theoretic results, because those results are so beautiful, and it's also very important in this direction. So yeah, for 3 manifolds, yes, I mean generators. For example, if you have non-prime 3 manifold, you can do some kind of Dan twist along the connect the 2 spheres. Or if you have like a cipher manifold, you can think about the automorphism group of the base. So basically, let me see. I would say that if the 3 manifold is geometric, then the generators are pretty well understood. Yeah. So, but I don't, as far as I know, I don't know like a very clean theorem saying like in 2 dimensions, like the Dan twist give you a set of generator. Because 3 manifold is more complicated. You have geometric piece, different geometric pieces. Yeah. But we do have a very good control about them. Yeah. If you give me any 3 manifold, it's not too hard to find a set of generators. Okay, and let me spend some time talking about gauge theoretic results. So in gauge theory, people love to compare the topological category with the smooth category. And this question is also important in dimension 4, because as I mentioned, the comparison between these 2 categories, the difference between these 2 categories first appears in dimension 4. There is no much difference. There is no essential difference in lower dimensions. Okay, so to study this question, let's consider the mapping class group in the smooth category and the mapping class group in the topological category. So let me just put a T here to indicate it's in a topological category. And well, so as I mentioned, we don't have much understanding of the smooth mapping class group in dimension 4. On the other hand, we do have a very good understanding of the topological mapping class group, where the manifold is simply connected. Because in this case, it's this topological mapping class group is actually isomorphic to the automorphism group of the second homology, preserving the intersection form. Okay, so for a form manifold, you have an intersection form given by the cut product. Then classical theorem by Queen states that this is actually every automorphism that respect this intersection form can be realized by a homeomorphism, and it's unique up to continuous isotopy. Okay, so yeah, so we do have a very good understanding about the topological mapping class group. And so, so I think one of the first results in this direction is given by Donaldson and Friedman-Morgan, stating that for many algebraic surfaces, this IM can be non-surjective. So meaning that that means there are some homeomorphisms on the manifold which cannot be smoothable. So that means it's not isotopy to a smooth map. It's not isotopy to a diffeomorphism. Okay, so this is proved by using Donaldson theory. So basically, Donaldson invariant, you can it's an invariant for smooth form manifold. You can sort it as a polynomial function defined on the homology. So if an automorphism on the homology can be realized by a diffeomorphism, it must respect this Donaldson invariant. So this is how they prove that there are many homeomorphisms which cannot be smoothable. Yes, so case 3, automorphism can be realized by the diffeomorphism if and only if it respects the homological orientation. So you consider the maximal positive subspace of the intersection form. If automorphism respects the orientation of this three-dimensional space, then it can be realizable. Otherwise, it cannot be realizable. So it's an index 2 subgroup. The image is an index 2 subgroup. Yeah, and so yeah, and another result proved by Danny. So like was almost 30 years ago, I guess. Yeah. So there exist exotic diffeomorphisms on form manifolds. So for many form manifolds, this forgetful map can be non-injective, meaning that there can be two diffeomorphisms which are continuously isotopy to each other, but not smoothly so. Okay, so that means that's the exotic diffeomorphism. Maybe so this result is proved by studying the family gauge theory. So if we have let's say if we have a diffeomorphism from M to itself, so one thing we can do is just form the mapping torus. So just take the product and quotient by 0x identified with 1fx. Okay, then this is really a so this is a fiber bundle over S1. Then one can study. Okay, so gauge theory can be applied to this family setting. You just treat it as a whole family of four manifolds parameterized by a circle, and you can compute the either Donaldson invariant or Seiberg-Witten invariant, and conclude that this family is a non-trivial family in many cases. And then you compare with Quine's result and state that there are many exotic diffeomorphisms on this kind of connected sums. Okay, and on the other hand, yeah, this is a wonderful result, and there has been many generalizations of this result, trying to find exotic diffeomorphisms on all kinds of four manifolds. But for a long time, people cannot find exotic diffeomorphism on an irreducible form manifold, or symplectic form manifold, or algebraic form manifold. So people cannot find that. A reason is that So what's the reason? A main reason is the following. In dimension 4, pretty much the only way we can prove something is irreducible is to compute its gauge theoretic invariant, like Donaldson invariant or Cyber-Witten invariant, numerical invariant. And there is a vanishing theorem stating that if you have certain kind of connected sum, then the number of solutions of these PDEs must be 0, something like that. And as you can see, this only applies when the expected dimension of the moduli space is 0-dimensional. So, but in that case, the moduli space for this whole family becomes 1-dimensional, and it's trickier to study 1-dimensional moduli space. Well, it's 1 dimension is not too bad, but still it's trickier than just counting numbers. So it's trickier to study this 1-dimensional moduli space and conclude that this is non-trivial bundle. Okay. On the other hand, there is, I think last year, there's been a breakthrough in this direction. Oh, sorry, I forgot. Somehow I didn't mention the name. This is also proved by Baraglia-Kono. So the same authors here. So last year, Baraglia and Kono, they wrote a very nice paper studying the Steno operations on the Cyber-Witten, on the Bao-Fu type invariant. Use Steno operation to study 1-dimensional moduli space of the Cyber-Witten equation, and they successfully prove that for many elliptic surfaces, there are indeed some irreducible four manifolds. And I think it's still an open question whether this exotic diffeomorphism can be made symplectic, or I don't think they can be made algebraic, but it's a still open question whether these diffeomorphisms, these Torelli diffeomorphisms, can be made symplectic or not. Yeah, that would be a very interesting question. Okay, and also another result proved by Baraglia-Kono, I think 2 years ago, states that there exists some simply connected four manifold whose mapping class group is not finitely generated. Okay, so as I mentioned, this phenomenon doesn't happen in higher dimensions and lower dimensions. Higher dimensions because of Sullivan's result, and lower dimensions because we have a very good control of the generators. Okay, for example, we know the mapping class group of a surface is generated by like 3 or 4 Dan twists. Okay, yeah. So this is again a special phenomenon in dimension 4, and another result proved using gauge theory is this field of homological stability. So as I mentioned, the cohomology or homology of the classifying space, they correspond to characteristic classes of manifold bundles. So people want to understand this. People want to understand this homology of a classified space. One classical way to do this is to take connected sum with like Sn cross Sn, or for surface, just increase the genus, take connected sum with torus. And there is a stable range. In lower dimensions, there is a higher stability result stating that this homology will eventually stabilize if you add enough genus. And then people can use other machinery to compute the stabilized homology. Okay, so that's a way to compute, to control the homology of the moduli space. However, well, in higher dimension, also similar result hold by Gracious and Oscar Randall Williams. So on the other hand, this fails in dimension 4. One can construct many examples for which this sequence never stabilizes. So the maps, no matter how large is this n, the error is never an isomorphism given k. Okay. So yeah, in other words, you cannot use this technique to compute a specific homology group of a diffeomorphism group of the classifying space. Okay. Yeah, and so then maybe let me ask any questions so far before I move on to non-gauge theoretic parts. Okay, all right. Okay, so let's move on. So yeah, and now let's continue. So it turns out that there is a closely related object with diffeomorphism group, namely the embedding spaces. So if you have a submanifold, you can consider if you have a submanifold of a four manifold, like a surface or a curve or like a three-dimensional submanifold, separating or non-separating, you can consider this kind of various embedding spaces. The space of embeddings from a lower dimensional manifold to a higher dimensional manifold. Okay, so yeah, so for example, there are many different variations. Like you can consider just all embeddings. You can consider the so-called neat embeddings. Neat embedding just means that both the domain and the target have boundary. The embedding sends the boundary to the boundary, the interior to the interior, and we consider all embeddings which are fixed near the boundary. So we fix a specific embedding near the boundary. Okay. So and also we have the space of framed embeddings, namely embedding equipped with a trivialization of the normal bundle. Okay. So these are all different versions of embedding spaces. And by the isotopy extension theorem, it turns out there is a fibration relating the diffeomorphism group of the complement and the diffeomorphism group of the whole manifold and the embedding space. Okay, so this is a fibration. So basically, yeah, this is essentially isotopy extension theorem. So you can study this. There is long exact sequence relating the homotopy group of these three objects. And another way to use embedding to study diffeomorphism is to show that a certain diffeomorphism is not isotopy to the identity by finding some specific submanifold which is taken to a different submanifold by this diffeomorphism. Okay? So you know this diffeomorphism group acts on the embedding space by composing. So if a diffeomorphism sends some submanifold to a different submanifold, then we can conclude that this diffeomorphism is not isotopy to the identity. Okay? So this is a classical way to distinguish diffeomorphisms. As we can see, there are many applications when the dimension of n is 2 or 3. Okay? We can study embedded surfaces or embedded three manifolds. Okay, right. Yeah, and so talking about surface, embedded surface, I would like to talk a little bit about Gabai's four-dimensional light bulb theorem, because this is one of the breakthroughs in smooth four-dimensional topology in recent years. So let me introduce some notations first. So let's consider two smoothly embedded surfaces, okay, R and G. So here we assume G has genus 0, so it's an embedded sphere. And we say this G is geometric dual of R if the self-intersection number of G is 0, namely the normal bundle is trivial, and if this G and R, they intersect transversely at a single point, okay, namely the geometric intersection number of this G and R, they must be 1. Okay. So they have no more, they have just one single intersection. Okay. So let's call a geometric dual. And also, when we study the case sigma has positive genus, another condition is useful. We say R is G in essential if the fundamental group of this complement of G in R maps trivially to the fundamental group of the complement of G in M. Okay? So now we're ready to state Gabai's light bulb theorem. Well, before stating this, maybe let me draw a picture of why do we call it light bulb theorem? Because, okay, there is in lower dimension, this is a well-known well-known result stating that, okay, so pi 0 of embedding space I cross S2. Okay, this is trivial. Okay. Yeah. So how to interpret this as light bulb? Because, okay, so let's think about, you have a light bulb here, okay, so light bulb. Yeah, so you can draw some funny art, okay. So suppose you have a light bulb, then you can think the complement of the room of the light bulb in the room is this I cross S2. And you have an embedding of this chord inside this I cross S2. Then it turns out that you can, without moving the light bulb, you can always make it into a standard picture. Okay? Because you can just go below the light bulb and unknot this whole thing. Okay? So a special case of this Gabai's light bulb theorem is basically the same. You just change this D into this D2 cross S2. This one. Yeah. Okay. So this is a four-dimensional version of the light bulb theorem. The version I stated here is a slightly variation of that result. It states that given two embedded surfaces, both closed, which are homotopic and have a common geometric dual, assume two conditions. First, the fundamental group of the ambient four manifold has no two torsion, and both surfaces are G inessential. Okay. The second condition is automatically true if you just think about embedded spheres. But for higher genus, this is a necessary condition. And under these two conditions, one can show Gabai proof that R is smoothly isotopic to R prime. These two surfaces are just isotopic to each other. Okay. So why is this a very important result? Because this is one of the few positive results in smooth four-dimensional topology. So what do we mean by positive results? In smooth four-dimensional topology, people define all kinds of invariants to prove like two four manifolds are not diffeomorphic, and let's say two embedded surfaces are not isotopic by computing different invariants. And for a long time, the only way to show two four manifolds are diffeomorphic or two surfaces are isotopic is just constructing them directly. You just construct either by Handel calculus or by some direct construction. But Gabai's result is a different kind. It's a positive result, meaning that you just verify these two conditions, then you know that the surfaces are isotopic to each other. You don't need to explicitly construct the isotopy. Okay? This actually gives renewed hope that maybe this kind of topological methods can lead to progress in classification in smooth 4D topology, at least under some extra condition, like there is a geometric dual or something. Okay, this is why people are so excited about it. And so because it's so important, people try to generalize it in many different directions. For example, can we remove one or two conditions in this theorem? Can we, for example, the two torsion condition about the fundamental group, it turns out that Hannah Schwartz proved that this is actually necessary. She discovered a pair of embedded surfaces with a common geometric dual, embedded spheres actually, with common geometric dual, which are not smoothly isotopic to each other. They are not even concordant to each other by the so-called, they are distinguished by the so-called Freeman-Quinn invariant. And this has been generalized to light bulb theorem with two torsions by Schreitman and Teichner. Okay, so they successfully remove the first condition. In that case, there is additional obstruction called the Freeman-Quinn invariant. Okay, so still, yeah, that's good. Yeah. So this is the light bulb theorem. Any questions? Okay. Yeah. And another direction trying to generalize this light bulb theorem is to one can study surfaces with boundaries, because if you study knot theory, if you study three-dimensional topology, you love four manifold with boundary because then you have more freedoms to construct all kinds of examples. The boundary can be a knot, right? So you can choose your favorite knot and study the surfaces bounded by this knot. And so people want to study manifold with boundary or embedded surfaces with boundary. And the first, maybe the most important case is embedded disks, right? So yeah, and of course, this is a very natural idea. Gabay tried to generalize the light bulb theorem to embedded disks, but soon after, he discovered the following result. It states that if we consider this M0 is the boundary connected sum between S, let me draw this picture. I think this is a very interesting example. So we consider this boundary connected sum. It's kind of funny four-dimensional picture, okay? So we consider this S2 cross D2 boundary connected sum with S1 cross D3. Okay, so it has two parts. Then there exist two embedded disks which have common geometric dual, and they are homotopic relative to the boundary, but they are not isotopic to each other. And actually, the construction is actually easy to describe. So D0 is just the standard embedded disk here. So it's like this. So this is D0. Okay. And what about D1? D1 is actually how to construct the other disk. To construct the other disk, we consider as embedded three-dimensional disk. Sorry, I cannot distinguish these two D2 and D3 in the picture. It's hard. Anyway, this is an embedded D3. And then what do? We pick an arc. Let me use the color chalk. Okay. So let's pick an arc going from, let's say, the center of the two-dimensional disk, and it intersect transversely with the three-dimensional disk, and go along a non-trivial loop and connect to the boundary of this three-dimensional disk. Okay, so this is an arc in a four manifold, starting from the interior of this D0 and intersect transversely with this D3 in the interior and go along here and go back to the boundary of the three-dimensional disk. Okay. Then what do? We let D1, since we have an arc here, we can draw a tube along this arc and do a connected sum between this D2 with the boundary of this D3. We just do this connected sum, and this is D1. And it turns out that D0, it's not hard to prove that, since this arc, you can just up to homotopy, you can just move this arc out and then just shrink it back. So D0 and D1, they are homotopy to each other relative to the boundary. However, they are not isotopic to each other. Gabay proved this by studying the so-called Dex invariant. Okay, so following early works by Dex, who studied embedding space when the codimension is large. In particular, Dex studied the space of embeddings of arcs in four manifolds, one-dimensional manifold in four-dimensional manifold. Okay, so Gabay compute the Dex invariant of these two disks and show that it's non-zero, so they are not isotopic. Yeah, and in particular, this shows that the light bulb theorem is not true. Well, at least if you just do the naive version of the light bulb theorem to disk, it's not true. And Dex invariant is an obstruction. Yeah, and maybe let me talk a little bit about the Dex invariant. They are not even as continuously isotopic, because Dex invariant can be defined in a topological category. Yeah, you can study configuration space, yeah. Okay, so let's define the Dex invariant. Okay, so given two embedded disks in a four manifold, we assume they are Let's assume they are homotopic to each other relative to boundary. Then let's just take a generic homotopy from D0 to D3. I won't try to discuss what generic means. Basically, you perturb it into so that it's smooth and satisfies some transversality condition. And now let's fix a decomposition of this three-dimensional disk into a two-dimensional family of arcs. So basically, I'm drawing a two-dimensional picture, but it's like this. You can decompose this three-dimensional ball into a union of one-dimensional arcs, parametrized by two-dimensional disks. Okay. Then, then we can restrict this homotopy of to each arc and get a family of immersions parametrized by the two-dimensional disk. So here, we can get a family of immersions instead of just family of continuous map or smooth map, because the Hirsch-Smale theorem, which states that you can perturb this family into a family of immersions, as long as there's no bundle theoretic obstructions. Okay? So we have this map, and it turns out that the space of immersions it contains the space of embedding as an open subset and some lower dimensional strata. The codimensional two strata are those immersions with a single double point. So if we choose H to be generic enough, then there exist only finitely many T's such that these arcs are not embedded. And each of them has a single double point. Okay, so when you have a single double point, when you have a double point like this, then you get a element in the fundamental group. Because let's say we fix the base point to be point here, then you can just go here, go along this non-trivial loop, and go back. Okay, so that gives us an element. That gives us an element in the fundamental group. Let's denote it by G. And so we have finitely many elements in the fundamental group. The Dex invariant is just the sum of these elements. Okay, so we discard those identity elements. We just take the sum of those non-contractible elements. So let's define as the Dex invariant. It turns out that if you choose a different homotopy H prime, then H and H prime you can pull them together and form a map from S3 to your three manifold. That's some element in pi 3. And you can do the same thing and construct a homomorphism from pi 3 to this abelian group generated by the fundamental group. We need to move out by the image of this Dex homomorphism to ensure that this invariant is well defined, independent with the choice of H. Okay? So so that's the Dex invariant. And as I mentioned, so if you just naively translate Gabai's Leibov theorem to disks, it's not true because Dex invariant provides a further obstruction. And actually, so there are generalizations in this direction, Kosanovic, Techner, and Schwartz. They generalize four-dimensional Leibov theorem to embedded disks with common geometric dual, taking Dex invariant into account. So basically, under some mild assumptions, they prove that if two embedded disks have geometric dual, for example, they have common geometric dual in the boundary, and if their relative Dex invariant equals 0, and the free band Queen invariant also equals 0, then they are smoothly isotopic to each other. Some result like this. Okay, yeah. The Dex invariant for maps of two spheres, well. Yeah, you can think Friedman-Quinn invariant essentially as an analog for Dex invariant of two spheres. Yes. So it's basically sort of the same theorem. I'm not sure. I mean, it just looks similar, but the definitions are not quite same. So, and also this version of Leibov theorem is still not I mean, there are still some technical conditions people try to get rid of. So it still has some room to improve, I think. Yeah, actually, I think Hannah updated her preprint like half a year ago. Yeah, making some improvement of the main result on archive. Yeah, okay. Well, I think I think the timing is good. So maybe, so let me end the first part of my talk here. And in the second part, I will try to talk about the configuration space, how are configuration spaces related to all these invariants, and what are our attempts to understand these invariants to refine it. And yeah, so let me mention some of our recent results. Let's generalize this DEX invariant to study closed surfaces. Well, we focus on the simplest example, which is just the product of a surface with S2. Okay? So for example, T2 cross S2. Then let's consider the set of embeddings in a fixed homology class. So namely, its projection to sigma, it has degree 1, and its projection to S2 direction has degree d. Okay, so we fix a homology class. Then it turns out that given any two surfaces in the same homology class, we can define a relative DEX invariant between these two surfaces, which satisfy some nice properties. First, it's invariant under isotopy. So if you have two embeddings which are isotopic to each other, then the DEX invariant is 0. And it's additive. Well, so, and also, this is invariant under diffeomorphisms. So if you have a diffeomorphism which is homotopic to identity, then it preserves the relative DEX invariant. Okay. Also, well, if we just look at these three conditions, you may say, okay, we can just set everything to be 0, sure. but the first condition, given any G, there exists some embedded surface and some diffeomorphism, such that this diffeomorphism takes the embedded surface into a different one, and the relative DEX invariant equals G plus G minus. Okay? So in particular, F and identity, they are not isotopic to each other because they take this embedded surface into a different one. Okay? D is S2 direction. So for example, like, yes, the map to sigma has degree 1. So so the simplest example we want to consider is like sigma equals sigma cross a single point embedded into sigma cross S2. This belongs to 0 because it has degree 0 in the S2 direction. Okay. Then you can take like parallel copies of S2 and take connected sum that give you something in sigma d. Yes, well, base point is an issue, but another issue is that to construct diffeomorphism, like, okay, so to prove this F, to construct such F, we need that F, we need that sphere, yeah, basically, yeah, so, yeah, something like that, yeah, or you can say, yeah, if you, basically, if you have a geometric dual, you can see you have an embedded sphere with self-intersection 0. In that case, you have a freedom to do a lot of interesting things to construct diffeomorphisms. Yeah. Okay, so yeah, so this is the DEX invariant for closed surface. So what's the idea? The idea is the following. Well, the idea is kind of naive. So okay, we have a, okay, so let's say we have two embedded surfaces. We want to understand that are homotopic to each other. We want to understand whether they are isotopic to each other. How do we do that? Okay, let's first try to isotope the 0 cell, okay, which is trivial. Then we isotope the 1 cell, which is also okay because for one-dimensional submanifold in four-manifold, homotopy implies isotopy. Okay, so you can just do isotopy so that the two embeddings equal to each other on the 0 handle and the 1 handles. So they are only different on the two-dimensional cells. Okay, so that's exactly what we do here. We fix a handle decomposition. We decompose the surface into 0 handle, 2G1 handles, and a single 2 handle. We do an isotopy so that the two embeddings coincide each other on the 0 and the 1 handle. Namely, they are only different near in a very small two-dimensional disk. Okay, then we just remove the tubular neighborhood of the 0 and the 1 handle, and define the DEX. Then by doing this, we get embedded disks into the complement, right? Then we just define the DEX invariant in the most naive way. Just define it to be the relative DEX invariant of the disk. Okay, but there's some problems here. There are two technical difficulties. One is that remember we define the DEX invariant only for homotopic disks, for embedded disks which are homotopy to each other. So I1 prime and I2 prime, they may not be homotopy to each other if you choose a wrong isotopy. Okay, so that's the first thing. And the second thing is that the isotopy may not be unique. So we apply an isotopy so that the two embeddings coincide each other on the 0 and the 1 handles. So the isotopy may not be unique. And if you choose a different isotopy, how to guarantee that the result do not change, right? So basically, in order to overcome this problem, we need to carefully study pi 1 of this embedding of these 1 handles, maybe, let me just say 1 handles. We have 2K1 handles, or 2G1 handles, into the complement of 0 handle, H0. Okay, so because basically, 0 handle is fine because it's more or less it's just a point. But now 1 handle, you can have non-trivial loop of isotopies. So we need to carefully control this group and understand that elements, if you change the initial isotopy by a non-trivial element here, it doesn't change the final answer. Okay, so yeah. Okay, yeah. So that's the DEX invariant, and so this gives us some corollary. For example, if you consider this product manifold, then there exists a homomorphism from this mapping class group to Z infinity, infinite copies of direct sum of Z, which is surjective, and it remains surjective if you restrict this homomorphism to the subgroup of maps which are homotopy to identity. So if you consider all diffeomorphisms of M which are homotopy to each other, homotopy to identity, you still get an infinite rank subgroup. Okay, so in particular, if you have any subgroup in between these two groups, it is always of infinite. It is always infinitely generated. Okay, so so this is another result about infinite generation of mapping class groups. This doesn't happen in lower dimensions. It happens in dimension 4. Okay. Yeah. And yeah, so the idea is also not hard. You just consider this standard embedded surface I0, and you just consider the relative DEX invariant between I0 and Fi0. That gives you a homomorphism from MCG0 to Z infinity. This is not the homomorphism stated in the corollary. We need to do some algebraic modification in order to extend to the whole mapping class group. Okay? But basically, that's the idea. You just consider the standard surface and think about the relative DEX invariant between the standardly embedded surface and its image under a diffeomorphism. Okay? And another result is yes, actually that's the hard part, and it's done in Gabai's paper. Gabay proved that these two disks, they are not isotopic to each other, but there is a diffeomorphism carrying one to the other. Yeah, we can just embed this submanifold into M and extend by the identity. The two surfaces are just equal each other on the complement of this picture, and in the disk, they are just like this. And when you restrict to disk, they are just like this too. So we don't need to do any calculation. We just refer to earlier calculations of Gabay. Yeah. And another result is that let's consider the set of isotopy class of embedded surfaces which are geometrically due to this point across S2 and has mapping degree D in the S2 direction. Then it turns out we have a complete classification of such surface up to isotopy. It turns out that the Dex invariant give a bijection between this FD and this group. This group is what? This is the subgroup of this free abelian group, which is generated by elements of like G plus G inverse. So basically, what does that mean? That means we have a standard. Okay, so let's see. So we have a standard embedding. So it's just like this. Okay. And now you can take parallel copies of S2 and smooth out the double point. This give you a standard embedded surface in a given homology class. Okay, so that's the standard one. And using the Leibniz theorem for disk, you can basically prove that everything is just obtained by this kind of self-referential disks. So it's like this. So you just draw different. You just do this, repeat that trick to modify this embedding on two-dimensional disk. And that's a classification, okay? So yeah, so the key ingredient in these theorems are Leibniz theorem, which is the positive, which is the powerful positive result. Okay, yeah, and now, okay, so you can see that there is a word configuration space in my title, and you may wonder, where is the configuration space? I have spent so much time talking about everything, and how does configuration space appears? Okay, so here it is. Let's consider the configuration space. The configuration space we are going to consider is a following specific version. We consider a manifold with boundary. We pick two different points on the boundary, and we put two different inward tangent vector. And we define the configuration space of k points. Really, there are k plus 2 points. The first one is just x plus. The last one is just x minus. And the middle ones are points in the manifold. These points are all required to be different to each other. Okay, they are not allowed to collapse. And each point is equipped with a unit tangent vector. Okay, so we are just thinking about the configuration of like, okay, so we have x minus, v minus, x plus, v plus, and you have like some points like this. So this is a element in the configuration space. Okay. It turns out that this space is non-compact, even though M is compact, because different points can collapse to each other. You can do compactifications. There are different versions of compactification. For the purpose of Dex invariant and the W3 invariant that I will discuss later, it's easier to use the so-called simplicial compactification. So due to Sinha, so that's a specific compactification which has a co-simplicial structure. So namely, in particular, it's a stratified space. The strata 1, correspond to subsets of 0 to k. So, okay, you have this. So basically, you keep track of the relative directions of 2 points when they collapse to each other. Okay, and in particular, if you consider this simplicial compactification of the configuration space for an interval, you get this standard simplex, k-dimensional simplex, 2k copies, because each point you have like a positive tangent vector or negative tangent vector. But let's just pick one component, okay? And yeah, that gives us a standard simplex. Okay? Now, why do we care about it? Because now, if we consider the embedding space from arc to M, we consider the space of embedding from this interval to M, then there is an evaluation map going from this embedding space to the space of maps from delta k to ck prime. Basically, it takes like f is this evk takes f to the map which sends t0, t1, tk plus 1, v0, vk plus 1 to ft0, ftk plus 1, f star, v0, f star, vk plus 1. Okay, so just take this map, okay, and it can extend it. This map can be extended to the compactification, and it turns out that it preserves the stratas. Okay, so here map means the space of strata preserving maps. We don't consider it's we only care about those maps which preserve each strata, sending each strata to the corresponding strata. Okay, and now by a deep machinery called embedding calculus by West, Good Willie Klein, and in this case Sinha, this map is highly connected. It induces isomorphism on the first k-1 homotopy groups. Okay. So in other words, if you want to understand the first few homotopy groups of the embedding space, you can study the homotopy group of this mapping space, the strata preserving mapping space on the right-hand side, okay? Which is easier to understand because the right-hand side, there is a spectral sequence going from the homotopy group of configuration spaces that converges to the homotopy group of the right-hand side. So the right-hand side is more accessible from homotopy theory. Okay, so now let's return to the Dex invariant. Okay, also called a W2 invariant by Bartnik-Gabay. So let's consider two embedded disks, D0 and D1. And as before, we just decompose the disks into one-dimensional families of arcs. Okay? Then by this decomposition, we get a loop in the embedding space. And okay, so we have this loop of embedding space. We consider the evaluation map to the configuration space of 2 points. Okay. And oh, sorry, I missed this pi 1. There should be pi 1 here. Pi 1 of mapping space of this. Okay. So pi 1 of this mapping space. And this pi 1 can be computed using a spectral sequence from the homotopy group of the configuration space. And when these two disks are homotopy to each other, one can just study the spectral sequence and redefine the Dex invariant using essentially comes from this spectral sequence. Okay. Yeah. Yes. So that's the Dex invariant. Bartnik-Gabay also call it the W2 invariant because it studies the configuration space of 2 points. Okay. As you can see, because we are just counting like double points, right? And yeah. And well, then Bartnik-Gabay further studied another invariant called a W3 invariant. So what's that? In their initial paper, they study the specific manifold S1 cross D3 and consider two embeddings from three-dimensional disk to this manifold, which are both standard near the boundary. Okay, they're just like a point cross disk. Then again, they decompose this three-dimensional disk into like two-dimensional family of arcs. Then, just like before, we can get a map from S2 to this to the space of embeddings. Just use the just sends the upper hemisphere to using I0, using the restriction of I0, and sends the lower hemisphere and send the lower hemisphere using the restriction of I1. Okay, and they define an invariant called the W3 invariant. So basically, it's defined by starting this evaluation map from pi 2. As you can see, right, alpha given element in pi 2 of the embedding space. Then we have this evaluation map to pi 2 of this mapping space. Like this is the mapping space between configuration spaces of 3 points. Okay, so this is delta 3, this is C3 prime. And then by repeating the spectral sequence argument, they construct a specific map to a quotient ring of this polynomial ring with 2 variables. Maybe let me explain a little bit about why does this happen. What's this? So, okay, we care about pi 2 of map delta 3 C prime M. Okay, yeah. So this is the strata. This is the space of strata preserving map from delta 3 to C3 prime, pi 2 of that. So you can think about it as a map from delta 3 cross delta 2 to C3 prime M. So you can imagine, so from here, it's not hard to see that it's closely related to the 5th homotopy group of the configuration space of 3 points. Okay. But this compactification do not change the homotopy type. So you just study this usual configuration space of 3 points without compactification. So we think about this. Okay. So what is this funny ring? Okay, so first of all, let's think about pi 3 of these 3 points. There are two specific elements, W12 and W23 in pi 3. So how to construct them? So W12 means you fix the first point and the third point, and you let the second point go around the first point. That gives you some element in pi 3, right? And also you can do W23, meaning that you fix the first point and the third point, and you let the second point go around the third point. That's pi W23. Okay? And you know M is not simply connected. It has a fundamental group. So you can consider the fundamental group of M acting on these elements. So the fundamental group acting on W12, the fundamental group acting on W23. These are 2 elements in pi 3. Then you can take the y-hat product and get an element in pi 5. Okay, so that's how they consider this, how they define the W3 invariant. So basically, it's the y-hat product of these winding elements. Okay, so yeah. And using this W3 invariant, they prove a very remarkable result. The mapping class group of S1 cross D3 is infinitely generated when M is a product of S1 cross D3 or S1 cross S3. And actually, they later generalize it to arbitrary closed hyperbolic form manifold. This is the alpha, beta, they are just powers of T1. So this element correspond to this element is just correspond to T1 alpha, T2 beta. Alpha, beta are just integers. Yeah, the fundamental group of this M is Z, right? So you just consider the action of the fundamental group on these winding elements and take the y-hat product. Yeah. Right. Mm-hmm. Mm-hmm. Uh-huh. It might be not injective, right? Yes, so here actually the invariant can be defined for, as you mentioned, it can, I think it can be defined for like immersed three-dimensional disks like that. Yeah, I think, well, for, no, for if you have immersion, then it depends on the direction, I think, of the decomposition, because you want to avoid the double point to be in the same eye. But if it is indeed embedding, then you can choose any decomposition. They're all homotopy to each other. Here, they are just considering this embedding of embedded three-dimensional disk. So the direction doesn't really matter. Yeah, and so as I said, so the proof is that you take the standard embedded disk in M and define a map from mapping class group by sending F to the W3 invariant between I0 and F compose I0. So the diffeomorphism takes this standard cross-section to some other funny disks. Okay? And also this implies the unknot S2 inside S3 bounds infinitely many disks. Okay, so S2, so let me mention this. So so a corollary, as a corollary, if you consider the unknotted, there exist infinitely many di's such that boundary di equals this unknot. Okay, so this doesn't happen in lower dimension. If you consider unknot in S3, it bounds a unique disk up to isotopy relative to the boundary. But in higher dimensions, this is not true. And also, this result is independently proved by Watanabe using configuration space integrals, which I will talk about soon. Okay, now let's move on to the work of Watanabe on Smale conjecture. So the Smale, I'm not sure. I think I'll call it Smale's question because I'm not sure whether Smale actually conjecture this, have a conjectural answer. So the question is the inclusion a homotopy equivalence? Okay, if you think, you can think about the diffeomorphism group of n-dimensional sphere and its isometry group, which is just the orthogonal group. Oh, sorry, I should put SON here because I'm thinking about orientation preserving diffeomorphisms. So is this inclusion a homotopy equivalence or not? Equivalently, if we consider the diffeomorphism group of an n-dimensional disk, is it contractible or not? Okay, and so the answer depends on dimension, of course. In dimension 2, the answer is yes, proved by Smale. The answer in dimension 3 is proved. The answer is also yes, proved by Hatcher. In higher dimensions, as I mentioned, the path component of diff dn, one correspond to smooth structures on Sn plus 1. So this immediately tells us that in many dimensions, whenever there is an exotic sphere, there is an exotic diffeomorphism in a dimension lower. So even for those dimensions, there are no exotic spheres. You can find some exotic element in higher homotopy groups. So the conclusion is that the answer is always no in dimension greater or equal than 5. So this inclusion is never a homotopy equivalence in higher dimensions. In other words, there are interesting family of diffeomorphisms on the disk fixing the boundary. Okay. Well, as you can see, these are pretty old theorems. And after Hatcher's work, the only open case is dimension 4. This is the dimension where you cannot use lower dimensional technique, and you cannot, the higher dimensional technique also doesn't quite work. But eventually, the n equals 4 case was proved, disproved by Watanabe, stating that this inclusion is not a homotopy equivalence. Okay? And so I will spend the rest of my talk discussing Watanabe's work and how we understand it. Okay, so first let me define an object A2K. So it's a vector space over Q generated by trivalent graphs with 2K vertices, and really it's an isomorphism class of trivalent graphs. Okay, and more out by the so-called IHX relation. So if two trivalent graphs are the same everywhere outside this small region, and they differ from each other by this local picture, then they just sum up to 0. Okay, so I'm pretty careless about the signs here. There are some sign conventions in this graph complex which I ignore. Yeah. Anyway, so you can define this. This is a finite dimensional vector space depending on Q, and Watanabe proved that there exists a surjection from this diffeomorphism group to A2K. In particular, this A2K is non-trivial when K is, for many cases, first starting with K equals 2. So that means the diffeomorphism group of 4-dimensional disk has a non-trivial fundamental group. There is and actually is even non-trivial after tensoring with Q. It's an abelian group. And it's non-trivial. Okay. Yeah. So this is an amazing result. Maybe let me talk about the invariants. Okay. So this is the configuration space in integral. Yeah, it's proposed by Consavage and studied by many people. Yeah, and I think it has been like 30 years. Yeah, including Essilor, Singer, Borthaus, Cooperberg, sorry, another type of Cooperberg, Thurston, and Leskopp, yeah, and many people. Yeah, and in a simply, let's consider the simplest case. K equals 2 case. Oh, sorry, again. So it should be A4. Okay. So A4 is generated by the complete graph with 4 vertices. So it's just like this, K4. Okay, so we have four vertices, and each pair is connected by an edge. Okay, and so let's try to sketch the idea of this integral. Given an element in the fundamental group of D4, we can use it as a clutching function and form a smooth disk bundle over S2. Okay, just glue 2 standard disk bundle together. After multiplying this alpha by some multiples, we can assume E prime is framed, meaning that the vertical tangent bundle, the tangent bundle of the fiber direction has a trivialization. Okay. And we can also extend it to a Euclidean bundle. So the fiber is not a disk, but it's a Euclidean space. Okay? But the transition function is not linear. It's a diffeomorphism from R4. It's a compactly supported diffeomorphism from R4 to itself. Okay? We want to develop some invariants such that to show that this bundle is non-trivial. So how to do that? Let's consider the configuration space of n points, n different points, okay, all on the same fiber. Then one needs to do compactification. In this case, the Fulton-McPherson compactification is easier to use because it gives us a manifold with corner. It's easier to do integrals. Okay, and then now let's think about this. Suppose the transition function is a linear function, then we can subtract 2 points, any 2 points in the same fiber and get a vector. Right? This is no longer true for this bundle because the transition function do not preserve the linear structure on R4. However, we still have a map from the boundary of the compactification to S3. Why is that? Because in the boundary, we are adding points which collapse to each other. So they are infinitely, they are very, very close to each other. Right? So you can take their relative direction using the framing, using the trivialization of the vertical tangent bundle. So we have a map from the boundary of the configuration space to S3. We pull back the volume form on S3 to get a three form on the boundary of the compactification. And you can compute the Ram cohomology of the configuration space and show that this three form can be extended to a closed three form on the whole configuration space. Okay, let's call it W. This is called a propagator, so it's a three form, closed three form on the compactified configuration space of 2 points. Now let's consider the configuration space of 4 points. Why do we consider 4? Because this graph has 4 vertices. We are basically thinking about an embedding of this graph into your bundle. Okay, so we have we have 4 vertices. So that gives you C4. And for each pair of integers, we have a forgetful map from C4 to C2, which just forget all the components except the i's and the j's. Okay, so we have 6 maps altogether. Okay, and now what do? We just pull back the propagator. That's a 3 form by these 6 maps, and get 18 form on this total space, and we just integrate it. Okay, so let's do a simple calculation. Why does this work? Because okay, so the dimension of E, oh, sorry. Again, my bad, this is another typo. We are integrating not over E, we are integrating over the configuration space. C4 E. Okay, we are doing this integration. This should be integrated over the whole configuration space. And why does it work? Because, okay, what's the dimension of this? This is, okay, so the configuration space of 4 points, that means 4 cross 4, plus the base is S2, so it has dimension 2. So this is the 18-dimensional manifold. And each is a 3 form. You have 6 projection map, so the numbers match up. Okay, so 18 equals 18. So you can do integration and get a number. And that's the definition of I, roughly speaking, in this simplest setting. Okay? Of course, the hard part is to show that this I is actually non-trivial. It's actually surjective. That requires a construction of disk bundle over spheres which are boundary trivialized but not trivial. So you want a disk bundle, a smooth disk bundle, which is trivial when restricted to the boundary, but non-trivial. Okay, Watanabe did this using the so-called clasper surgery. So basically, I don't have time to explain the detail, but basically you consider a bunch of embedded Hopf links and Borromean links. Basically, for each vertex, you consider a Borromean link, okay, with 3 components: S2, union S2, union S1. And for each, then you link these Borromean links using the edge. Okay, so you link them together as like a Hopf link. You consider non-trivial linking number. So you get a family of framed embedded links, okay, inside D4. Then you do a family surgery. So you just take out the tubular neighborhood and you glue in another solid torus using the framing. So by doing this, you get a family over 2-dimensional torus. And it's not hard to prove that this family is trivial when you restrict to the 1 skeleton. So it induce a family over S2. So yeah, so that's the clasper surgery. And another hard part in Watanabe's work is to compute this invariant for that family essentially using these linking numbers and like this triple linking numbers of this Borromean link and Hopf link, and conclude that it's non-trivial. Okay, so that's the hard work. Yeah. Anyway, so Watanabe succeeded and showed that this is surjective. Okay, and now, so one observation is that any boundary trivialized disk bundle is topologically trivial. Why is that? Because the structure group is sitting inside the homeomorphism group, of the disk relative to the boundary. However, by the Whitney trick, this is actually contractible because you can squeeze, since it's standard on the boundary, you can squeeze everything to the origin. You don't care about the smoothness because you are considering homeomorphism group here. So the homeomorphism group of a disk relative to its boundary, it's actually trivial, it's contractible. So that means any boundary trivialized disk is topologically trivial. So actually, this configuration space integral detects exotic disk bundles. Exotic means it's topologically trivial, but smoothly non-trivial. Okay? And this sounds very, very exciting because this invariant doesn't quite use gauge theory. It doesn't use partial differential equations. You can see it just uses configuration spaces. And a natural question is like, gauge theory can also be used to detect exotic bundles. For example, those exotic diffeomorphisms constructed by Danny, you can just take the mapping torus and get an exotic bundle over S1. Okay, so that's another exotic bundle detected by gauge theory. So we have exotic bundle detected by configuration space integral. So what's the relation of these two exotic bundles? Do they have the same nature or do they have different nature? The answer is they are indeed quite different. Okay, to explain this, let me talk about the formal smooth structure. Okay, so let's consider a topological manifold. Such manifold always has a topological tangent bundle, which is a fiber bundle with fiber 4-dimensional Euclidean space. Okay, really, it's you can obtain this by considering a suitable tubular neighborhood of the diagonal in the product. Here you need to in order to get an actual topological fiber bundle instead of micro bundle, you need to use the Kister-Mazur theorem to make it into an actual fiber bundle. Okay, now this is a fiber bundle. A formal smooth structure on M is a vector bundle structure on this topological tangent bundle. In other words, you want to reduce the structure group from the homeomorphism group of R4 to the group of linear transformations. Okay, and similarly, you can define this formal smooth structure in a family setting. If you have a topological bundle, you can also define its vertical tangent bundle. Again, it's a topological bundle with fiber R4. It's not a vector bundle. And a formal smooth structure on this topological bundle is just a vector bundle structure on its vertical tangent bundle. Okay, and there is in higher dimensions there is a very famous result by Kirby Zimmerman and Benir Leshoff. It's called a smoothing theory. It states that in dimension not equal to 4, formal smooth structure is essentially equivalent to smooth structure. Namely, if you have this linear structure on the tangent bundle, this is essentially an H-principle kind of result. You can patch this linear structure together and get a smooth structure on the manifold. This works in any dimension not equal to 4. However, in dimension 4, this is not quite true. For example, any of those exotic smooth structures on 4 manifold, they are all the same as formally smooth manifolds. Okay? Yeah, and what we can prove is that 2 years ago, that there is a topological version of the configuration space integral. Let me denote it I top. That is defined for it can be defined for all framed topological disk bundle over general base or formally smooth bundle over spheres. In other words, it's a configuration space integral that only depends on the formal smooth structures. So you actually don't need a smooth structure on your form manifold. You just need a linear structure on the topological tangent bundle, and it coincides with the classical configuration space integral when the bundle is actually smooth. And it induces a surjection between from the homotopy group, from the rational homotopy group of top 4. Top 4 means the homeomorphism group of R4 preserving 0 to this AK, okay, to this graph homology. And an important step in this is to construct a well-behaved Fulton-McPherson compactification, not using smooth structure, but just using formal smooth structures. Okay, yeah. And so there are some applications. For example, using this, as we know, AK is non-trivial for many cases. That gives us a lot of non-trivial homotopy group of top 4. We didn't know much about this homotopy group of top 4 before. The Kirby-Zieberman invariant corresponds to some element in pi 3, yes, yeah, and pi 4, sorry, yeah, and we can construct a lot of higher homotopy groups, elements in the higher homotopy groups. We also we can prove this inequality regarding the rational homotopy group of homeomorphism group of S4. And in particular, this implies this top 4 and homeo S4, they are not rationally homotopy equivalent to any finite dimensional CW complex. In particular, top 4 is not rationally equivalent to O4, and the homeo S4 is not rationally equivalent to O5. Okay, and also, if you consider the difference between top 4 and O4, your quotient O4, this map is known to be 5 connected. This is essential. This is important in smoothing theory. For example, Quinn used it to prove that any two diffeomorphisms which are homotopy to each other become isotopic after sufficiently many stabilizations. It used this 5 connectedness. And as another corollary, we show that this map is not 7 connected, even rationally. Okay. And another application is that you can, using this non-trivial homotopy group, you can consider some characteristic classes for topological bundles, which obstructs the existence of formal smooth structure on topological bundle. So this can be thought as an analog to Kirby-Zieberman invariant, because Kirby-Zieberman invariant correspond to H4, correspond to some non-trivial homotopy group of top 4 more O4, and it obstructs. It's the only obstruction for a single form manifold that has a formal smooth structure. Okay? A single form manifold has a formal smooth structure if and only if its Kirby-Zieberman invariant is 0. Okay? And this characteristic class can be thought as a family version of that, using higher homotopy group of this top 4. And also another result is that, as I mentioned, we want to compare the diffeomorphism group and the homeomorphism group. There's this natural forgetful map. And it turns out that using this result, we can prove that this map for any form manifold is not rationally 2 connected. In particular, it's not a weak homotopy equivalence for any form manifold. So the space of smooth structure has a non-trivial second homotopy group. Okay? So in other words, there are non-trivial holes in this space of smooth structure on any form manifold. This is different with lower dimensions. In lower dimension, this is always a homotopy equivalence. So this is what we mean by saying that in lower dimension, this smooth category and the topological category, they are essentially the same. They are essentially the same in this very strong homotopy theoretic sense. Okay? All right, and also, so it's, I believe it's some work in progress by some other group of people. Yes, it is not true, also not true in higher dimensions. But the complete proof, I think, is still in progress. You need to use some rational punctuating class by Michael West. Yeah. Yeah, and let's return to this question. Okay, so what's the difference between the exotic bundle detected by configuration space integral and and the gauge theory, okay, we have three moduli spaces: the moduli space of smooth manifold, the moduli space of topological manifold, and the moduli space of formally smooth structure, formally smooth manifold. And it turns out that exotic phenomenon has two types. The difference between smooth and formal smooth, that's special in dimension 4 and it's detected by gauge theory. And the second type of exotic phenomenon, it happens in all dimensions greater or equal than 4. It's essentially between the difference between the formal smooth structure and topological. It's bundle theoretic. And what we prove is that this configuration space integral only detects exotic phenomena of dimension of type 2. So these two exotic phenomena detected by gauge theory and configuration space integral, they are more or less like perpendicular to each other. Okay? Yeah. And well, so there are some open questions, interesting, but I'm running out of time, so let me just quickly say about it. So try to generalize Dex invariant for general form manifold. Try to use W3 invariant to understand the mapping class group of more form manifolds. Try to use configuration space to study mapping class group of S4, T4, and something else. And try to find more conceptual way to compute these invariants. You know, these invariants are computed in a rather geometric way, kind of ad hoc for in every setting. So one may want to find conceptual way or more algebraic way to compute this invariant, and try to generalize Watanabe's work to graphs which are not trivalent. Okay, so I think that's all I want to say. Yes, thank you very much.